Welcome to AP Chemistry at Honeyniga High School. I'm Brian Brown, and today we'll be looking at section 20.3, introducing voltaic cells and understanding the parts of a voltaic cell. Now, in a spontaneous oxidation reduction, or redox reaction, electrons are transferred and energy is released. And as a spontaneous reaction, it automatically happens. You put the piece of zinc inside the solution of copper nitrate, and you start to see the formation of copper ions on the outside of the zinc strip. Spontaneously happens. We don't need to do any work to make the reaction occur. Now, because we have an electron transfer occurring here, and electricity is basically harnessing a flow of electrons, if we set our system up correctly, we can actually create a battery. So a voltaic cell, or a galvanic cell, is basically setting up a situation where we can harness that flow of electrons by passing it through some external device, through a copper wire that goes to a light bulb or a radio or whatever, to do useful work. So since we have a spontaneous flow of electrons, we can harness that flow to do useful work. Now we call this setup a voltaic cell or a galvanic cell. Voltaic and galvanic cells are synonyms for each other. We're talking about the exact same thing. So what we're really doing is using a spontaneous redox reaction like you saw on the previous page, but that's all happening together in one beaker, and the electron transfer is happening on a particle level. Well, we can't really harness that flow of electricity, but if we can separate our reactions into two half reactions and connect the two to make a circuit, we can end up harnessing that flow of electrons. Now, a typical cell looks like this. Now, the oxidation is occurring at the anode, negatively charged, since basically the electrons are produced here. So in a voltaic cell, the anode is always negative. Now that doesn't mean anodes are always negative, but in a voltaic cell, the anode is always negative, because there's also a type of reaction where it's non-spontaneous, and we make the reaction happen by hooking up a power source to push electrons through and make the reaction occur. In that particular case, the anode is not going to be negative anymore, but that's for later in the chapter. Now, the reduction is always going to occur at the cathode, and that's going to be positively charged in a voltaic cell. Now, it gets confusing, so how do you remember all this stuff? Well, there's a couple of acronyms we're going to end up looking at. First is ANOX, anode oxidation. Second is a red cat, reduction, cathode. So ANOX reminds you oxidation occurs at the anode. Red cat reminds you that reduction occurs at the cathode. Another way to think of this is match the vowels and consonants. A and O, both vowels. R and C, both consonants. Now notice that the electrons flow in this particular case, like in all voltaic cells, from the anode to the cathode, because there is an arrow here that's basically showing the direction of the electron flow. Well, it's not a coincidence. Fat cat reminds us that electrons always flow in a voltaic cell from the anode to the cathode. Once again, we're looking at a voltaic cell when we use this acronym. So when you look at a diagram, if you see electron flow, that tells you where your anode is and where your cathode is, because the flow of electrons will start at the anode and will end at the cathode. Now, in order to make this circuit work and the reaction go, we need basically a complete circuit here. And that's where the salt bridge is going to end up coming in, and the other parts of our diagram here. But what's happening in a oxidation reaction? Oil rig, oxidation is loss. So in an oxidation reaction, you're producing electrons, and those are going to need to go to our reduction reaction, where we're gaining electrons. Now, oxidation is happening at the anode, so that's where we're making electrons. And at the cathode, we need electrons, so electrons have to flow from the anode to the cathode. Now, once one electron moves in this situation, we have a problem, because now we're going to end up with electrons moving in one direction. We have one area that's going to be electron rich, another area which is electron deficit, and to keep pushing more electrons into electron rich environment is a problem. So once one electron moves, if we don't have a complete balance of charge throughout everywhere in all of our beakers and at all instances, this reaction is going to immediately stop. So it's very important that we have our other components beside our anode and our cathode here. One, we need a connection between the anode and the cathode, and that's our copper wire that here is running through a switch and a voltmeter. And two, we've got this tube in the middle. And that tube is what's known as a salt bridge. So what you need to understand is, once one electron moves, we're going to have an imbalance of charge, and the flow of electrons is going to immediately stop. So if we want this reaction to keep progressing, we need to set up a very specific situation. Now, well, I'll pick up in a second. Let's look at that salt bridge and then we'll come back to my other idea. Therefore, before we have to have a salt bridge. Now, the purpose of the salt bridge is to maintain charge neutrality. And basically, it's a connection between our two half cells. So notice it's a tube that runs from one to the other and it's filled with a liquid, and that liquid contains a salt. So right in the middle here, we have our salt bridge. Now, what's happening as one electron moves away from our anode to our cathode, we're turning zinc into Zn2 plus. So into this solution, we are dumping in Zn2 plus. So we had zinc nitrate originally in this beaker, and we're going to be dumping in more zinc. So basically our zinc anode here is being converted into zinc ions. Well, that's going to cause a charge buildup in our anode compartment or in our anode half cell here. So what we have to do is basically counterbalance that increasing charge by adding a negative charge. So notice our nitrate is flowing down into there. So as we create positive zinc ions, sodium and nitrate ions, which are in our salt bridge, are going to move. The nitrate ions, which are negative, are going to move into our anode compartment and help maintain charge neutrality. Now on the flip side, when our electron moves over to the cathode, copper 2 plus ions come in here and pick up electrons and get converted into copper. So copper is going to start to plate out on our copper cathode here. Well, that means we have copper cations that are leaving solution in our cathode compartment. Well, that's going to cause a deficit of positive charge. Well, how do we prevent that charge buildup from becoming a problem? Well, our sodium ions are going to be attracted into that now negatively charged solution, and that's going to maintain our charge neutrality. So notice we get a flow of nitrate and sodium ions to help maintain charge neutrality. And the salt bridge really needs to contain a salt that contains cation anions, but more importantly, you need a salt that's not going to react with the solution that's in each compartment. Remember, we have nitrate in one side, along with zinc ions, and the other side we have copper ions and nitrate. Well, sodium with nitrate isn't going to precipitate out, and zinc with nitrate isn't going to precipitate out. So sodium nitrate would be an appropriate salt for our salt bridge in this particular battery. Remember, any salt can work as our salt bridge, but you want to make sure the salt that's in there doesn't cause precipitation, because then those ions are going to leave, and once again, you no longer have charge neutrality. Your reaction's not going to work. So the big thing about our salt bridge is we need ions that don't precipitate out. And notice the cathode is on the right, and that's the direction that our sodium ions flowed. Now, that's not a coincidence. The name cathode comes from the fact that cations are flowing towards it. So when you have a voltaic cell and you've established what your anode is and what your cathode is, you can quickly establish the direction of flow of your salts in your salt bridge, because the positive cation is always going to be moving towards the cathode. The negative anion is going to be moving towards your anode. So we have a direction of movement of electrons. We have movements of ions in numerous places here. But notice our cations are always shifting to the right towards our cathode, and our anions are always shifting, in this case, to the left towards our anode. So we have a movement of ions, both in solution and in the salt bridge, in two different directions here. So another thing you need to understand about this cell is which direction things are going to be moving through the course of the cell. And one really, really important idea here, because this is a very common misconception with electrochemistry. People think electrons basically are flowing through this solution like that. And because it's a circle, it makes a circuit, and therefore the reaction goes. Electrons don't flow like that. You need to understand that electrons are flowing in one place. In this reaction over here, as zinc metal is becoming zinc ions, it's producing electrons, and those electrons are flowing through here. Now, what's happening over here is the Cu2 plus is picking up those electrons. So the electrons are only flowing to the cathode, and they're being attached to the copper ion to make copper metal. They are not flowing through solutions. When solutions conduct electricity, it's not moving electrons through the solution. What's happening in solutions when you're conducting electricity, or in this case making a circuit, is a movement of charged particles. In this case, it's our sodium going that way and our nitrate going that way. And since everything is all connected together here, we do make a circuit. But remember, electrons only flow through the metal. In solution, we have movements of charged particles. Now, instead of a salt bridge, we can also just have a porous barrier between the two that allows our ions to move back and forth between the two sides and maintain charge neutrality that way. So sometimes we have a salt bridge. In other situations, all we have is a porous barrier between the two. Alkaline batteries really just use a porous barrier between the two. Now in the cell then, electrons leave the anode and flow through the wire to the cathode. We established that. Remember, the electrons are moving through the wire. As the electrons leave the anode, the cations form dissolve into solution at the anion compartment. So over here, our zinc atoms are becoming zinc ions. So what do you think is going to happen to the mass of our anode as it loses zinc atoms? Well, this is what we call an active electrode, because zinc is actually, the electrode itself is made out of zinc, and those zinc atoms are actually involved in the redox reaction. So in this particular case, the mass of the active metal in our anode is going to decrease. So our anode is going to become lighter here if we were to weigh it before and after. Now on the flip side, we have an active cathode. Over here we have copper ions, and those things are being stacked onto our piece of copper. So as the electrons reach the cathode, and the cations in the cathode are attracted to the now negative cathode, and they grab those electrons and become metal copper, those electrons are taken into the cation, and the cation is deposited now as a metal on top of the cathode. So over time, the mass of our cathode is going to be increasing. So the mass of the active anode decreases, and the mass of the active cathode increases as this reaction occurs. Now, one of the things that the book really doesn't do as good a job of doing, because different books do this in different ways, but this is a pretty standard notation that you sometimes see on the AP test and in chemistry class. So I want to make sure you're aware of it. Voltaic cells can be rather complex things to diagram. So a way we have of abbreviating is this cell notation here. On the left side of our double line, and the double line represents our salt bridge between our anode and cathode compartment, we're going to have our anode reaction, our oxidation. And that's our substance becoming a positive ion typically. And then on the right side of our double line, we're going to have our cathode, which is our reduction reaction, which is in most cases a charged ion becoming a neutral substance. So what we can do, rather than write the whole redox reaction and so forth, is we can use the double arrow to represent the salt bridge between the two, the single arrow to represent the boundary between the electrode and the solution where the reaction is occurring, and then we simply state what's becoming what. And it's a much quicker way than writing the full redox reaction. So if we want to use this cell notation for this reaction, remember it's anode on the left, cathode on the right, alphabetical order here. What's happening at our anode is Zn is becoming Zn2+, and what's happening at our cathode is Cu2+ is becoming Cu. So this is a easier way to describe this voltaic cell than to just diagram the whole thing or to write the complete balanced redox reaction. So this is a common standard way to represent voltaic or galvanic cells that you need to be familiar with. Now, we've talked a lot about the cells and we've looked at all the parts, but you don't really get this unless you can draw and diagram it. Now, the first one I want to take you through, so I'll walk you through step by step, and you can complete it on your worksheet. But the second one, I want you to pause and try it yourself. And it's a little bit more complex situation, but everything is the exact same. So just do what you did in the first place, and you'll see that you get it right on the second place. Now, in order to diagram really what's happening throughout our entire voltaic cell, we're going to end up with a picture that looks like what we've been looking at on the previous slides. Well, first we need to figure out what a redox reaction is that's involved. Then we need to place our anode, and then we can look at the reaction that happens there and label that part. Then we can do the same thing for the other side. And then finally, we can describe the salt bridge. So those are the steps we're going to go through here. Now, it says to draw the voltaic cell for the reaction between magnesium and zinc nitrate with a potassium nitrate salt bridge. Now, magnesium and zinc nitrate. So that's Mg, plain magnesium, that would be solid. And it's zinc nitrate, so we've got zinc ions. Now, the nitrate is just going to be a spectator here. So really what we have is a reaction between Mg and Zn2+. Now we know Mg is going to become its ion, which is Mg2+, and we know Zn is going to become it's metal, which would be plain old Zn. Now notice it's, to balance this thing, we have to split in half and balance everything. But in this case, it's a pretty simple one. It is a +2 to +2 situation. So each reaction, each half reaction is going to involve 2 electrons. So it's a 2 electron equal electron transfer. So the balanced reaction ends up as is. So that's the redox reaction that's happening overall. But we want to split it up and look at where it's happening individually to truly understand the situation. So now that we've got a reaction, we're ready to look at our actual cell. Now, first thing you want to do is establish the anode. Remember, the idea for establishing the anode was fat cat. Electrons flow from the anode to the cathode. Notice in the diagram, our electron flow is designated. So that means our anode has to be over here at the beginning. And remember, in voltaic cells, anodes are negatively charged. Anode, anti, negatively charged. But remember, that's only voltaic and galvanic cells, spontaneous reactions, not electrolytic, non-spontaneous reactions. We'll get into that later. Now that we know that's the anode, we can think, okay, what happens at the anode? Anox. Anode is oxidation. So when I look at our oxidation numbers up here, 0 and +2, +2 and 0, what's being oxidized? Well, it looks like magnesium is increasing in oxidation number. So that is our oxidation half reaction that's going to be happening over here on the left. So this is our oxidation compartment, or oxidation half cell, and we know Mg is becoming Mg2+. To balance that, we need to show our electrons. Mg, to balance Mg2+, well, we need 2 electrons on the right to get the charge on both sides to equal. In this case, both equal 0. So 2 electrons on the right, well, that makes sense. It's oxidation. Electrons should be lost. They should be on the product side. Now, that means what's happening in this compartment is we have Mg becoming Mg2+. Well, where are we getting our Mg from? Well, we've got an electrode there. That electrode was made out of magnesium. That would provide our magnesium metal that we're going to convert into Mg2+. So that's what's happening in that compartment. We've got a magnesium electrode. So our anode is actually a strip of magnesium, and it's being converted into a solution to magnesium ions. So we need to start with something like magnesium nitrate as our solution over here. And we're going to be just dumping over time more magnesium ions into that. Now we've taken care of our oxidation compartment. Now we're ready to go to step 5. Do the same thing for the other side. Well, our electrons move towards the cathode. So over here is the cathode. That's positively charged. Red cat. Cathode is reduction. So this is our reduction compartment. And reduction is the thing where the oxidation number is going down. That's Zn2+ to Zn. Remember, we need to add 2 electrons on the left to make that happen. So that's what's happening in this compartment. So once again, we have another metal. So no surprise that our cathode electrode is going to be a piece of zinc metal. And what's happening here is zinc ions in solution. So we must have something like zinc nitrate dissolved in the water over here. Those zinc ions are going to be plated onto the zinc cathode over time. So now we've taken care of both compartments. All that we've got left is describing our salt bridge. Now remember up here it says we have a potassium nitrate salt bridge. So we got KNO3 in there. Now, cations of potassium are going to be moving one direction. Anions of nitrate are going to be moving another direction. Now there's 2 ways to think about this, easy and hard. The hard idea, the real idea, what's happening over here is we have zinc ions leaving solution and becoming Zn. We're losing cations over here. Well, that would mean that this is going to become negatively charged. We can't have charge buildup. So that should mean that potassium ions should move over into this solution. And that would mean nitrate ions have to go the other direction. Well, it makes sense. If I'm putting in positive cations, I need to have a movement of negative anions of NO3- into there to, once again, maintain charge neutrality. So that's how you're really supposed to think about it. But to keep it simple, we already know what the anode and the cathode are. Remember, the cathode is named because cations move towards it. The anode is named because anions move towards it. So that's the easy way to see what the direction of flow is. So this would be our complete cell here. And we could go on to say that it looks like cations then are moving that direction, and anions are moving that direction. That's another thing we could diagram in this particular cell. So those are all the different parts of a voltaic cell that you need to understand. Now, I want you to try one. So I want you to draw the voltaic cell for the following spontaneous redox reaction between that's described here. So that is our redox reaction. And conveniently, I've already balanced it for you. So we don't have to go through that whole process. That's our balanced redox reaction. So that redox reaction is happening in our voltaic cell, and we have a potassium nitrate salt bridge. So pause the tape here and work through the same steps that I took you through on the previous slide to figure out what's going on here. So go through step 1, 2, 3, and so on. Step 1's done. Now you're ready for step 2. So pause the tape and give it a try. Okay, electrons flow from the anode to the cathode. So I've got diagrammed the electron flow, so I know over here's the anode. Anode is negatively charged in all voltaic cells. Remember, the anode is where oxidation occurs. And if you look at the top reaction, well, when I diagram this, I have I minus starting out as a -1 and becoming neutral. That's oxidation. So that must mean reduction must be happening here with my Cr2O7. And if you'll notice, 7, -2 each is -14. What plus 14 equals -2? Well, 12. So what is Cr here? Well, that must be a +6. And it's going to a +3. So yes, it is being reduced. Now, that means oxidation, my I minus reaction is happening on the right here. And my chromate reaction is happening on the left. Oops, I got it out of order here. So this is the reaction I've got happening on the right side, right here. Now, that's coming directly from this reaction up there. But usually this will be written simplified, because what's really happening here is we have I minus becoming I2. Well, to balance that, I need 2 I minuses, and that means I need 2 electrons on the right. So this is how you would traditionally write this. I wouldn't mark it wrong if you wrote it this way, but that's how you'll see it normally diagrammed. 2 I minus yields I2 plus 2 electrons. So that's what's happening on my oxidation side. Now, unlike in the previous reaction, we don't have a metal here. So this can't be an active electrode. It's got to be an inert electrode, something like platinum or carbon. So graphite or platinum. Usually you're going to see platinum here. It's a highly conductive metal that's non-reactive. It's going to work perfect. In this case, it's not active. It's not actually part of the reaction. It's just a site of the reaction. So what's happening, and that's one of the reasons this is a little more confusing, our reduction reaction, which is listed here, is happening in solution. So it's not happening in the cathode or in the anode, it's happening at it. So on the surface of our platinum, we're going to have electrons moving out of solution here, or I should say, electrons are needed on this side because they're on the reactant side. So electrons that are produced over here in this reaction solution are going in and moving over to there, and they're going to be picked up right here to make this reaction occur. So our electrons, once again, are just flowing through the wire, but now our electrodes themselves are not a part of the reaction. What's happening is the reaction that's there is happening on the surface of those electrons. So the right side is providing the electrons that the left side needs. But these reactions are not happening in the electrode. They're happening at the electrode and in solution here. Now, finally, we have the salt bridge, which it said was potassium nitrate. And remember, easy or hard, you can evaluate charge. This is negative going to neutral on the right side, so that means it's becoming negative deficit, so negative should be going into there. Well, the easier way to think about it is, remember, anions move towards the anode, cations move towards the cathode. So K plus is going to be on the left, NO3 minus is on the right. So our cations, in this case, are moving in that direction, and our anions are moving in that direction. And that's what this voltaic cell should look like. So that's what you should have got for your answer. And that ends our second set of notes from chapter 20.